Okay, so today we're beginning chapter 12, which is about rational equations and functions. And 12.1, the first section, we're going to model inverse variation. So we get to see a new type of graph. It's cool. It's really the final type of graph that we get to see. So inverse variation sounds like another variation that we covered this year. The variation we already did was direct variation. And who remembers what direct variation looks like? Direct variation, Tom? Okay, so it looks like a, what type of shape? Linear. It looks linear, and he says it goes through 0, 0, right? So the model, who remembers the model for direct variation? You don't need to write this. This is just a little scratch paper for me. Y equals x. Y equals x is direct variation, but usually for the model we put one thing in there. And that is, we put the m, or in your book this year uses a. Sometimes k is used. It is the slope, isn't it? And there's no plus b out there. So you could add plus 0 if you wanted to, but the y-intercept is always 0. So if this is direct variation, then what is inverse variation? Let me say this. If this is 1/2, what is the inverse of 1/2?
2, 1.
Good. So what did you just do? You did the reciprocal. You moved something to the inverse location, right? So what do you think is going to move if we have y equals 2x? What do you think? Is it the 2 or the x? I mean, right, if we move the 2, look at this. If we move the 2 to the denominator, we really have a 1 up in the numerator, right? So we have a slope of what? 1/2. So is that direct variation or inverse? Can you have a slope of half that's a linear equation?
Yes.
Yes, it's just a flatter line, right? So instead of moving the 2, we're going to say y equals 2 over x, right? And so we've moved the input, okay? So in inverse variation, the input is in the denominator. A is still called the constant of what? Constant of variation, good. Constant of variation. It is the one thing that isn't changing. We'll change the independent variable x, and then the corresponding dependent variable y will change, depending on the x, right? Okay, so because the input is in the denominator, there are values that are not going to work, depending on what the expression is that's in the denominator. This expression right now in the denominator is just a simple x. So Tom just said that the value you couldn't put in is 0. You can't put 0 in for your input because you would end up with what kind of an equation? Undefined, right? Now, why can a not equal 0? That's part of the rule here. What would the equation, what would the graph look like if a was 0? Everybody with your arms? Good. I see horizontal lines, right? Because you would just have y's are all at 0, y's are all at 0, and it's no longer an inverse function, which we're about to graph. It would just be a linear function, y equals 0. You wipe out the inverse if a was 0. And in this equation, x can't be 0 because it would be undefined. So that could change depending on the expression that's in the denominator. What if the denominator had x plus 1? Now what value may not be input? Good, -1, because x, -1 plus 1 equals 0, right? So there's a reason it can't be input. Okay, before we graph, which we're going to graph 2 of these today, one question you might be asked is, can you identify inverse variation just in the equation? And so this question is, which of these are direct variation, which is inverse, and are any of them neither of those? So direct, inverse, or neither. So what might a strategy be for somebody so that it makes it easier for you to look at this and say it's inverse or it's direct? What strategy could you use, Cassandra? So good. So you would isolate y and then look at it and say, where is my input? Right? So Cassandra just said, when you isolate y here, you get this. So is this inverse, direct, or neither? Does everyone see? The input is showing us this is inverse variation. And you can just abbreviate that in your assignment. Okay? And when we isolate y in example B, what does the equation look like? John?
If x equals 2 and 1.
But that's not isolating y. And that's not even a correct way to transform this, is it? How do you isolate y here? By y? And you get x equals 2y, and then divided by 2. So you really have y alone equals x over 2. So is this inverse variation? No? Is this direct variation? Or is it neither? What is the number in front of x here? Could I put a 1 here? So is this not y equals just 0.5x? What is this? Direct variation. What's the slope? No, the slope is not 0. The slope is 1/2. See, you can see it, 1/2. And maybe you're seeing it better when we change it to a decimal, but when you are dividing by 2, it's still direct variation. It's just a fraction. Your slope is just flatter, that's all. This is direct variation. If we were going to add the y-intercept, what number would we add? Y equals 1/2 plus 0, because there was nothing visible, it's 0, and that is a point on the graph, right at the point of origin, right? Okay, how about C? When you isolate y, what does this equation look like? Johnny? And so, is this direct variation, inverse variation, or neither? And it's neither because it has a y-intercept at -5. See that? If this wasn't here, we would have direct variation, just a slope of 3. But that is there, so it is no longer direct variation. Okay, one more. xy equals 1/2. So when we isolate y here, what do we have, Jenna? One half. Did you say dividing by x? Aren't we dividing both sides by x? So dividing by x. So is this inverse variation, direct variation, or neither? It's inverse. And if you don't know what to do with this is why I have it here. Because it always confuses people, like, what does it look like? It doesn't look like 1/2 times x. That would be direct variation, right? Some people prefer to write the 1/2 as a decimal, and now we see 0.5 over x. It's easy to see. This is inverse, right? We're dividing by the x. If you're dividing by x, you're really multiplying by the reciprocal, 1 over x, right? So the equation could also be written as 1 over 2x. That is 1/2 over x. It still is. So if you have an equation that has the x in the denominator and there's something else down there, the other stuff is just, they're just factors, that's all. It's still inverse. You may change it to a decimal, but you don't have to. This is still inverse variation. Okay, any questions on that? Okay, then let's go graph an inverse function. Okay, so you've not graphed one of these recently or anything? I don't know if you've ever graphed one of these. So what does a person use? What's a strategy for graphing when you've never graphed it? What you do, Matthew? Make a table. Okay, so we're going to get some points and see what it looks like on the graph. Okay. Before we say what we're going to use, what is the one number we can't use? 0. So we're going to say, as far as the domain goes, we can have all real numbers except x cannot equal 0. That's range. We'll see what happens when we do this. Okay, so we could put 0 as kind of the dividing line here. This is undefined. So we're not going to find a value, we're not going to see a point when x is 0. But what values might you plug in? You might put -1, even 1, right? So let's go ahead and plug this in. Let's start down here. If we plug in 1, what do we get out? 2 over 1? 2 over 1? 2 over 1.
2 over 1, 2.
It's just 2. 2 divided by 1 is just 2. 2 divided by 2?
1.
2 over 2 is 1. Good. Now 2 over 4, Kate. 2 over 4? Did you just say 2? You are totally inversed today. 2 over 4 is? 1/2. Okay. Let's go back up here. -1. So 2 over -1. 2 over -1. -2. 2 over -2. 2 over -4. Okay, there's something really interesting about dividing by our input. Because think about what other type of input could you put in here that would have a dramatic effect on the outcome, the y? Anybody think of a different kind of number than we just substituted? Squared numbers, I mean, that would have a dramatic impact. What happens when you divide by a fraction, right? Let's try that. What if you plug in 1/2? When you plug in 1/2, you get y equals 2 over 1/2. Or 2 divided by 1/2, which is 2 times the reciprocal, which is, I don't know why I just put that in the range. The 1/2 is the input. It goes here. And we got 4 out. Okay, let's go with a smaller fraction. Somebody give me something smaller than 1/2.
1/8.
1/8, he says. 1/8. Okay, let's try 1/8. When you divide by 1/8, you just flip the 8 up and you get 16. So the smaller the fraction, the bigger the output. Do you see that? What if I divided by 1, y equals 2 over 100? What would my output be? 200. See, it gets bigger. Okay, so that's interesting. Let's try it with the negatives. -1/2, I'm going to say 1/4 this time. So -1/2 gives us again -4. What does -1/4 give us? Good, -8. Okay, so let's go graph it. Is there anyone already graphed it? Pause the video and come back and see what it looks like. So the graph of an inverse function doesn't just give us one curve, it gives us 2 C-shaped curves. And you must show both. And these C-shaped curves have a cool name. It's kind of like parabola, but what do they call you if you're all have eaten a bunch of sugar? You're very hyper. So they're called hyperbola. It's not a hyperbola, it's a hyperbola, okay? There's one other thing we need to add. Notice that these C-shapes, they will never hit x equals 0. We already determined that. The only way for y to equal 0 would be if the number 2 actually was changed to 0, right? And is that going to happen?
No.
No, it's a constant. So y will never equal 0 either. Never equal 0. It could equal, anything positive on the right in quadrant 1 over here. It could equal anything negative in quadrant 3. Okay? There are 2 lines that we add to this. The lines that these C shapes will never cross. And in this example, because it's such a basic little equation, the lines are actually on the axes. But go ahead and draw them in. You might want to use a different color. So do you think it's possible we could shift these branches up or down or left or right? You think so? Yes. So when we do, these lines would shift. And these lines have a special name. They're called the asymptotes. Can you see that? Asymptotes. Okay? Be sure that you draw these imaginary lines into your graph when you have graphed your hyperbola. We're showing a sample of each of these types of graphs when the constant of variation is positive or when the constant of variation is negative. And there's your example. Right. Pause and take it down.